Mm, Very fine. Good morning, students. Today I came with another topic that is silicates that we will discuss in this session. Today we are discussing about the silicates. We will discuss regarding the formula and the name of that silicate and the structure analysis and the number of oxygen atoms per tetrahedron structures. And this is the most important thing regarding exam point of view. When we consider, first of all, we will learn how the formula will exist in this silicates. Let us have a brief introduction here also. Silicate, let's write like this: SiO, SiO, like this 5 times you have to write SiO and another SiO. And here we will given the charge obviously will be there, like decreasing order -4 and increase by +1 means -4 plus 1 -3, and this is -2 and this is -1, and the fifth one is this is 0. Obviously this is a neutral one. And when it comes to the number of oxygen atoms, 4 and decrease by 0.5, that means 4 minus 0.5, that is 3.5, and this is 3 and this is 2.5, and this one is 2. Like this way the formulas will exist. And when it comes to the naming system, the namings, I'll tell you a small trick regarding this. The trick is OPC 2D 3D. OPC 2D 3D. By remembering these 5 letters, we can give the names based on this. And here we will see the SiO4 minus. This is O, that is ortho silicate. Ortho, O means ortho, and this is P. P means pyrosilicate, and this is C. C here can be referred into two terms, that is cyclic, and the second one is chain can also be, and the remaining is 2D and 3D. These are the 2D silicates. 2D, that is sheet like structures, so those are 2D structures, and SiO2 is a 3D silicate. Like this the naming system can be done. And when it comes to structures, SiO4 is a exist in a regular tetrahedron structure. Like let's have a structure I'll draw here. Si is the central atom and two oxygen atoms. SiO4, the charge is -4, so each oxygen will contains negative charge SiO4, and this structure will exist. The wedge and these representations will be there, but these are not much necessary, but I am showing you how the tetrahedron will exist. This is a 4 chart, so this is SiO4 -4. This is a orthosilicate. And when it comes to number of oxygen atoms per tetrahedron, oxygen atoms per tetrahedron joining, like corner, we can say corner atoms. In exam point of view, they will ask you the corner atoms only. I forgotten to write the corner here. In the exam point of view, they will ask the number of oxygen atoms per corner regular tetrahedron. We will see the question solving session as well in the same video itself. So here this is this is only a single tetrahedron. Like this it will exist. Let me show you the how the tetrahedron will be. Like this, a tetrahedron. In top view I will show some diagrams as well in the further. This is SiO 3.5. You multiply with this 2. This is an empirical formula. So if you dimerize it, you will get a structure like this SiO, and -6 is charged, no? So like this it will exist. For structures it's taking too much time. For next diagrams I will take directly diagrams, so it will takes less time to complete it. So here we can see this is an each Si will form a regular tetrahedron, and here we can identify one thing, that is one oxygen atom is there in the corner between two. So here the number of corner oxygen atoms are 0 in the case of orthosilicates, where in the case of pyrosilicates this is 1. Let's remember this is the most important. So next, this is the cyclic structure. The formula is same for both, only the structure is, when it comes to a cyclic silicate or a chain silicate, I will show directly. I am taking for saving the time purpose. So here let's have a brief. This is the structure of cyclic silicate. We will see the cyclic structure here. The cyclic structure, let's consider this silicate. This is formula like if we here the cyclic structure is consisting of 3 SiO, so 9 O should be there. So 1, 2, 3, 4, 5, 6, and these circulars also silicates, only the dots of pink color, they are the SIs. So Si3O9 -6, this each minus charge will be there like this. So the charge will also be satisfied. So here we need to calculate the count the how many. Let's consider this silicate. It is joined with two more tetrahedron structures. The number of oxygens are this one and this one, and these two oxygens are not connected to any. So here the cyclic structures will have cyclic structures, cyclic silicates, two oxygen atoms. This is, let's move this structure to apart from here so that we can discuss the chain as well. Let's remove this. And when we have a cyclic structure, we have discussed this cyclic one. Let's have a this thing. So this chain one we will discuss here. See here in this structure here we are discussing the chain. This chain is consist of a particular things that are silicates. This is one tetrahedron and this is one tetrahedron, and this is like this. Some tetrahedrons were linked like chain structures, so that's why these are called chain silicates. So let's consider a middle, this one. So we can count the number of oxygen atoms which are in carbon. So this silicate was tetrahedron structure was linked with this atom and this atom. So this is also two chain silicates. Number of oxygens are 2. So we can, in the question he will ask you the list of silicates and he will ask you the number of oxygen atoms that are attached. So from here we can learn okay, that's we can remove. When we are moving to 2D, 2D silicates are like this. This 2D structures. I'll paste it here. For your convenience, I'm going to increase the structures now. So here what we are having is like, you can see this is a regular tetrahedron structure and this is a regular tetrahedron, and this is also like this, a 2D sheet like structure came. So when it's a 2D sheet, for example, let's consider this tetrahedron and let's count how many oxygen atoms, and these structures are oxygen atoms, 1, 2 and 3. So 1, 2, 3. So total 3 oxygens are attached. So here it is 3. And when it comes to 2D, 3D structures, 3D structures are SiO2 structures. Actually, it will exist like this, but it will get a more prominent structure when it is in this kind of structures. Actually, for drawing these structures, I can draw, but these are uh, time consuming, but and even structures are not much necessary in the exam point of view. So I'm directly taking the structures. So here we can see the silicon was attached to oxygen, 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 and this oxygen is directly attached to the some other. So this oxygen is attached to the some other, and this silicon is attached to some other, and this one is also will attach to the some other silicate. So here when it's a 3D structure, it will have SiO structure is like this. Now we have studied in the orthosilicates. So this oxygen will attach to some other Si, and this is some other Si. This is some other Si. Like this, each oxygen will be a corner for each other tetrahedron. So 4 oxygen atoms are there. So let's solve a few questions that have been asked in the JEE mains exams and GATE exam as well. And I'll take all the questions at it like this. Let's have a simple. Let's start with a simple question. I'm taking all the questions now only for the not interrupting again and again. Hope you understand. And direct questions will come from this topic, and this topic is very important for the exam point of view. That's why I'm taking very even some students asked me to do some clarification video. So let's see the a question here. A direct question has been asked here. The question is, how many oxygen atoms shared per SiO2 tetrahedral unit mineral? The mineral is given Si3O9, and this is charge negative -3. So okay, as we have seen, Si3O9 is belong to Si3O9. Where it will come? It will come if we multiply this with 3, Si3O9 will come. So it could be a cyclic or a chain. Even it is doesn't matter that even cyclic chain, cyclic or a chain silicate, the number of silicate in the silicate structure, the oxygen atom shared pair is 2 only. So the directly question is, we can answer it option A, that is 2. This is the correct answer for this question. Even without knowing the structure, if you know this a tabular form, and I'll mention this a proper table, that is a formula name and the number of oxygen atom per that I'll share through a tabular form which is available in Google Sheets. I'll provide this in the description of this video. And the next question that we can see, okay, see here in this question, the number of oxygen atoms shared in per the silicate tetrahedron, that is given a 2D silicate. This is two dimensional, so 2D. And this is cyclic silicate. Here he mentioned cyclic silicate, cyclic one, and a single stand chain silicate. So here you can consider it is a chain silicate. Let us see how many 2D, when it's a 2D structure, 3. So here 3. In this question only we have seen the uh, cyclic and chain, and both are consisting 2, cyclic and chain. The cyclic and chain structures are 2, and this is also 2. So the answers in the options he may give like this: 3 2 2, 3 1 1 1, 3 1 1, 3 2 1, 2 2 1, and like this he will give some options. You have to choose the correct option, that is 3 2 2. So the next question, this is an important question which has been asked in the GATE 2023. In even I appeared for this exam also, and this question is, let's see, the number of shared corners consisting oxygens. In the corners oxygen will be shared, otherwise silicate will not be shared. SiO4 units of the ortho I'll represent orthosilicate, and this is pyrosilicate, and the next one is cyclic and sheet silicate. Sheet means a 2D sheet. 2D sheet. So ortho we have discussed, that is 0, and pyro the next one is only 1, and the cyclic we have seen 2, and the 2D this is 3. So the option is 0 1 2 3. This is the answer for this question. So we can see the same numbers, the 0 1 2 3, and this is option A. This is the direct question, and this is a 2-mark question in the GATE 2023 exam. So hope this concept will be helpful for you in the exam session. Thank you for this. And if you want any kind of topics has to be revised or concepts will clear, you can do comment. I'll make video on it. Thank you.